Good morning. How's everyone doing today? So it is almost halfway. We're pretty much halfway through the semester. How are your classes going? How's it going with 1510 lecture? Have you had your first midterm? It's going okay. I'm glad to hear that. And it's pretty painful with a lot of classes. I agree. It's a tough point of a semester right now. If we were on quarters, it's kind of almost done. But yeah, 15 weeks right now, it's middle point is a tough point. So how did you guys do on your first midterm? Was it better than you expected, worse than you expected? Did you do okay? All right, I'm glad to hear that, Joshua. Yeah, I'm glad to hear that. And so far, so good. All right. Now, if you want to talk about either the lab or anything related to 1510 in general, feel free to let me know and reach out to me. I'm happy to provide help in any way that is possible. Okay, so our lab today is lab 7. And we are more than halfway done. Overall, we have 13 labs, right? So after lab 7, we have 6 more labs. So we're getting there. So just hang in there. This is about uniform circular motion. For this one, we actually are not falling behind with our class. We had already talked about centrifugal acceleration, and we had already talked about Newton's second law. So nothing to catch up there. So just to sort of remind us of these concepts we have already learned in class. If you have an object that is in circular motion, it's a uniform circular motion where speed doesn't change. However, the velocity, the direction is still changing. If you look at the velocity at this instant, it's pointing upward. If you like the velocity at a different instant is tangential to the path, right? So it's like this. Right here, the velocity is like this. You can see this velocity is changing its directions all the time. Now it must have an acceleration. So even though its speed is not changing, and that acceleration points directly towards center, and we call it the centripetal acceleration, AC, right? Centripetal acceleration. And that's velocity squared over radius r. If you want to represent that velocity acceleration using period, the time, which is what we will do in the lab, is we will keep counting. We'll use our stopwatch to keep track of the time. Eventually, we want to find out what the acceleration is. So you have the choice of either plugging, you simply calculate your velocity first using your period, and then you can plug that in and find your acceleration. Okay, so don't be too hung up on the final result here because you know how to calculate this. This is really just using v squared over r. Okay, so let's take a look at our pre-lab because that particular pre-lab is getting to how to calculate acceleration. So let's take a look at our pre-lab. So if this object is traveling with in a circular path at constant speed, now we know that's circular motion, and tell us the radius is 18 centimeters, which is 0.18 meters. And tell us about the period. Okay, period is the time it takes to complete one entire revolution, one cycle of motion. So it takes 29 seconds for the body to complete 50 revolutions. So how do I calculate the time for one revolution? What is T? What is capital T? How do I calculate capital T?
It would be 29 seconds.
It will be 29 seconds, and that is for 50 revolutions. Now, I want the time for 1 revolution. Right? Sorry. Capital T. Yes, divided by 50, right? So, and that gives you the total time it takes for 1 revolution. Very good, very good. So, now you want to calculate the linear velocity. And again, I want to show that you don't have to memorize any equations. You can just think about the meaning of these quantities and you can solve it. So linear velocity is, well, what's the linear distance it traveled over the time? So it traveled 1 revolution, it traveled 1 circumference. So that's, what's the circumference? 2 pi r over that much time. This is 2 pi r over v. That's your linear speed. And to get acceleration, you can do v squared over r again. So you can plug in numbers right here and plug in numbers v here, or you can plug in your v and do your numbers at the end, whichever way works. Okay, so if you do that, you will get r over t squared. So this is the equation we just saw in the slides. Okay, that is also the equation we will use in our lab to calculate the centrifugal acceleration. There is another, so this is a linear velocity. The magnitude is the linear speed. What about the angular? Sorry. What about the angular velocity? So how do I calculate omega? Do you still remember this from the lecture? What does angular velocity mean? Anyone? Change in rotation over time. Yes, very good, Cannon. So linear speed is our change in the horizontal distance over time, right? Or our linear distance over time. So this is our angular distance. Well, angular, how to describe the change in the angular position? Well, we use the angle to represent it, right? So if you go all the way around, instead of saying that it traveled 2 pi r, we simply say, well, it traveled a 2 pi. So the change in angular position over time. So that's simply omega. Omega times r gives you velocity. So they are related. Now, you probably have seen this quite a bit. There is an equivalent equation to use omega to write acceleration is omega squared times r. Okay, and that's also okay. Right? So either way, you can find your centrifugal acceleration. Whether you decide to choose v or you decide to calculate omega, you can always find the acceleration. I'll show you the final solution. So here I have tried to calculate my velocity. I actually calculate my omega first. Okay. And then I use my omega times r to get velocity, and then use v squared of r to get my acceleration. So you can see these variables, they're all connected. In what order you do them doesn't really matter. Okay, so how do I get the omega? Omega is the angular position changing, angular position over time. So simply use, okay, 50 revolutions, that's 52 pi's, go around 50 times. Then that is done in 29 seconds. So that tells me 10.8 radius per second is the unit for omega. So if you do unit analysis, notice that the radians is not a unit, okay? It simply is dimensionless. Okay, so when you do omega times r, you can see that this is radians per second. The dimension is really just 1/2 times r is meter. So we get meters per second, which is the unit for velocity. So radians, that radians does not going to alter or change your units. So just a quick review of our pre-lab. Now we're ready to do this, to take data. So what is the kind of the object we have? So we wanted to make an object go into a circular motion. To do that, we connect this object. This is object we're going to do, and make it spin around. So we're going to spin around in the circular path. Okay. And when's that centripetal force coming from? We attached it to a spring, and the spring will provide a centripetal force. So essentially, we want to be able to evaluate, is this force really is proportional to the centripetal acceleration? Is the spring force really providing that corresponding centripetal acceleration? So we want to be able to measure my force and measure my acceleration and then plot it, okay? Now, acceleration, we know how to measure. We use a time watch to measure the time it takes. But how do we, measure the force? There is an indirect way to measure the force. Is, okay, once it's spinning, obviously you do not have the pulley and the tension. It's just spinning by itself. But you will, after the spin or before you do the experiment, before you time it, you're going to run another hanging weight through a pulley and pull this object to a 18 centimeters mark, okay? So that's where it was when it was spinning. It's at that radius. So this is my radius. But how do I know how much force the spring is providing when it's that much long? Well, I'm going to drag it to the same mark. I'm going to hang that much mass to see where it could be balanced. So the weight of the hanging mass is going to equal to the force provided by the spring. Now, for example, if I'm hanging 5 pounds here, now which means the spring on the side is providing 5 pounds. Now, of course, the tension is also 5 pounds everywhere inside the string. Okay, so you can see this hanging mass is an indirect way to tell me how much force the spring is providing. Okay, so we're going to measure my force, and we're going to measure all the accelerations, and then we're going to put it all together. Let's take a look at the data table. So there will be 4 different trials because they will put 4 different masses so that you get 4 different centripetal force. Okay. They start out with 1,100 grams. That's really just 1.1 kilograms. Okay. And then they will make it into 970 kilograms, and so on and so on. So we'll have 4 different trials, and for these different trials, we're going to measure its acceleration. Now, notice me, it's very difficult, right, to measure it going all one way around because it's super fast. It will be more accurate if we can time it when it goes 50 rounds and divide that by 50 to get the time it takes to go all the way around once. Okay, so for each of those masses, the spin, the object they're recorded for 200 revolutions, but you only need 50 revolutions. So what you will do is we'll choose any 50 revolutions from the video, and you will use your stopwatch. You can use your phone to time it, and you will time it 3 different times so that it will give you a average, right? Okay, so we will go to our data and take a sort of a quick practice run to see how do we going to time it. And there are some uncertainties we want to add onto our table as well. For example, the uncertainty of the acceleration, we will get it from our time through error propagation. We'll talk about that later. The uncertainty for our force, because there are only 2 different variables here. We measure this, we measure this. The uncertainty from the force is from the uncertainty of our mass. Okay. So let's go ahead and switch to the video and we can take a look how they measured the uncertainty for the mass.
Our values are right, but we are not going to stop here. We'll back off the masses slightly and determine a minimum mass. But we want to ensure that we still complete the object, what we consider to be 18 centimeters.
Because our rotation is kept at 18 centimeters. So where would you call 18 centimeters? So there is a little range here that gives us an uncertainty. So the smallest mass you can add so that you will still consider that 18 is 440 grams as a show. That's your max, that's your minimum. And it will continue to find the maximum value.
Now we're going to find the maximum. And that's done by slowly adding masses until it is bigger, but still within a range in which we would call it 18 centimeters.
Okay, so here you have your max minus min over 2. That is your uncertainty for the mass. Okay. We will talk about how to do the force. Simply multiply that by G. You will get the delta, the uncertainty for the force. But we'll look at back at our theta table later. But now let's take a look at the
And that's it.
That we want.
Remember, your uncertainty is taking the max minus min divided by 2. And your best mass will be determined by the average of these two values. For the following accelerations, we will be timing with a stopwatch. Remember to time only once the object reaches 18 centimeters. It is impossible to maintain a speed consistently. So by timing 50 oscillations 3 times, we find an average time. As we cannot see time, this method of simply repeating multiple measurements allows us to determine a plausible max and min. Time your oscillations within any of the 200 rotations.
So this is our first trial with 1100 grams. So when the object passed through the 18 centimeters, there is a little tape. So you're going to hear a sound, the clicking sound. But sometimes, so you would want to start timing it once it has that clicking sound and then count 50 rotations. But sometimes it can go shifted away a little bit and you may not hear a sound, but we should still time it because that's still a 1 revolution. So use both your eyes and ears when we do the timing. So we're just gonna do the timing together. Let's see if we actually get very close results from one another. Okay. All right, so you can hit your
period. Make sure you start at various sections to capture a better average.
All right, I'm going to stop. I believe that's enough for us to get the time for 50 revolutions. So anybody would like to volunteer the time they recorded for us? So anybody got the time for 50 revolutions? Anyone? Okay, all right, yes. So I'm getting some answers. Now, sometimes it takes a little bit more practice. Now, if you get, let's say if you get 29.7, Milano, then you're not so sure whether it's correct, then do 50 count again. If this one seems to be obviously an outlier, then the other one, then you can delete this, consider this an outlier and use the other ones, okay? So are we timing each mass 3 times? Yes, we are choosing to do our timing 3 different times. Every time you count 50 revolutions. It gives you an entire video span of 200 revolutions. Now, which 50 you choose, totally up to you. Whichever sections you want to start your timing, that's totally up to you. So I only played for maybe the first 1.5 of the entire recording, okay? You're supposed to time it 3 different times. I'm asking for anybody had your time because I want to be able to compare my time to yours. So let's say now one of you timed 29.7 and I got 24.6. And let's say someone, and then you, let's say this are 3 times you have done. Okay, someone else does 23.9, for example. And then, well, you can just use these different trials 3 different times to get an average. Okay, so more, because that makes it more accurate, right? So you can get the average. And how do you calculate the delta t, which is the uncertainty of your time? How do I get the uncertainty for my time? What is the method that we often use to get the uncertainty? When we have a few different numbers, some of them are smaller, some of them are bigger. There's a maximum number, there's a minimum number. How do we get the uncertainty from those numbers? We do the delta t to be just like how we did our delta m, the max minus min over 2 method, right? We have a t max minus t min over 2. This is same to be RT max, and this is RT min, and divided by 2, and then you will get your uncertainty. Now notice that you will do the timing, and then your number every time you will have a different uncertainty. That's what we want. Okay, so do this, then you'll get your time, and then you can do the same thing for the other masses that show up later. Now you found your time for 50 revolutions for the 1100 grams. How do you get the period, which is the time for 1 revolution? Well, to get 1 revolution, you simply are going to divide it by 50. Okay, so this is what we're getting to. Going to the t average and divide by 50. That is your time for 1 revolution. And the uncertainty of that is also divided by 50, is the uncertainty of your 50 revolutions time divided by 50, and that is your delta capital T, okay? So to do the period, essentially, we want to be able to use that to find our acceleration. So to get our acceleration, you have the formula from before is 4 pi squared. This is constant. R is 0.18 meters and divide by the period squared. And the period is what you calculate here. Okay. And your acceleration and your uncertainty of your acceleration, how do you calculate? Still remember the error propagation rule? This is what we did in the beginning of our lab, lab 1. We talked about if you have a power, then because A is some constants, well, the constants doesn't count, is the power over t squared. So if you have a power, the relative uncertainties of A is the power times the relative uncertainty of t. Okay, so that will tell you what the absolute uncertainty delta A is. Delta A is your A number times Q times delta T divided by T. So that will tell you what the uncertainty for your acceleration is. That is this column. Okay, so that's how you get your acceleration. The force, you can get the force simply by using the mass times gravitational acceleration, G, to get your force in here. So if this is 1.1 kilograms, then obviously here would be 1.1 times 9.8 newtons. The uncertainty from that is your uncertainty from your mass times G. The uncertainty from the mass is max minus min, something like that divided by 2. That is from your mass. That's in grams, okay? Now, again, be very careful. You want it to convert it to newtons, so you have to convert the mass to kilograms and put it in there. So once you get all your forces and all your acceleration, you're ready to plot. So we are graphing F versus A.
How do we get the uncertainty for the added mass?
Oh, that was at the beginning of the video. Remember, they showed a max minus min method.
Okay.
They showed min 440 grams and the max, double check it. I don't know if I remember correctly. The maximum 470 grams, and that is your delta N.
Okay.
Yeah. But that is in grams, okay? So you need to convert that to kilos. Yeah, make sure you convert it. Okay, so that uncertainty just simply because we are considering that mass is to be at 18 centimeters, but where is it in T centimeters? Both within this range, you still consider that to be 18 centimeters. That gives you an uncertainty. So once you have all your data, you plot your force, okay, you plot your acceleration, and you will try to find a best fit line. So any prediction, what kind of a graph I will get? Would I get a linear graph? Or would I get a curved graph? If it obeys Newton's second law like this. So any predictions, what kind of graph I would get?
Linear.
Linear, yes. Because U is F equals MA. So what would the slope represent? Let's say I recommend that you use Excel to plot it. In Excel, you would choose a scatter plot. So the scatter plot would simply just put these dots on your graph, okay? Have a scatter plot. And you will add a trend line. In one of the options, you can also make it show equations. You do want to just show equations because I will tell you what the slope and y-intercept is. So you'll get something like y is equal to, now I'm just making up numbers, okay? So don't use these numbers as the actual data, plus 225, for example. So if I get something like this, and what is my slope?
$500.
Yes, so if and then y-intercept with 25. So what is the meaning of my slope? What is the physical meaning of my slope? Again, if it obeys Newton's second law, So here is my slope, right? You should be able to get a slope that represents the mass of the or circulating body, which is that little cone-shaped object you see earlier. So you should get the 500. Now if your forces is in newtons and your acceleration is meter in second per second square units, then you will get your slope, which is a kilograms unit. Now, which tells you your object should be also 500 kilograms. So that would be the meaning of the slope. What this object look like? What you're measuring is the object of this body. Okay, so essentially the slope tells you what the mass of this object is. So at the end of the video, they will put this guy on the scale and you can actually read its mass. And you can compare what you measured to what it reads and see if that had you have done a has the experiment verified. If it agree with each other pretty well, then you can conclude that indeed the force and the acceleration follows Newton's second law. Okay, so that's a verification of the Newton's second law in the lab. There is a question by Brian. Since you give us a chart, would we graph it ourselves? Okay, so I provide the graph, give you a graph, but graphing by hand requires you to be very, very careful. So I do want to say this and remind you that a lot of you did a hand graph, but it's sort of there, you're just guessing where everything is. And you need to use graph paper because to put your dot and your scale on very accurately, you need those really finer scales. So you cannot draw the scale yourself, it will not be accurate. So you can, of course, graph it yourself, but you have to use graph paper because you need to read the slope accurately from your hand-drawn graph. As an alternative, if you wanted to save yourself some time, simply you can use your computer to plot it for you. And the computer will also provide the scale, the slope for you, and you don't have to do it by hand. Hand graphing is good, it's good practice, but we already did that at our first lab. So for all the future labs, you can choose to use the computer graph as the alternative. It's more, it saves some time, it's also more accurate. Okay. So if I also get a y-intercept, any guesses of that what that might represent? What would the y-intercept represent? So I probably would not get a graph that's perfectly through the center. There's a little y-intercept. What kind of quantity that might be?
Acceleration.
Oh, okay, very good guess. So I'm trying to plot y f equals ma. So in a perfect world, I would get y is equal to kx, right? So which means the y is my f, the x is my a, and my slope is my k. But if I do get a little b, what kind of quantity it has to be? So this is where you can say, well, by dimensional analysis, what b has to be? It has to be the same physical quantity as kx gives me, or it has to be the same quantity that y gives me. So if y is in newtons, is equal to something kx plus 25 newtons. So this has to be in newtons. So the y-intercept has to be what? Has to be a force quantity. It cannot be any other quantities. Why is that? Because it is kx plus b is equal to y. And kx is my ma, right? So if you have an intercept, that has to be a force because they are on two sides of the equation. It has to represent the same physics quantities. So what might this force come from? To have the force from the spring and then make the object move, in the perfect world, that's the only force you get. But in real life, you might expect there might be some other forces. other forces could be some kind of friction that exists in your system, right? It could be some friction. So that's why you get a y-intercept. That's your friction. Very good, Brandon. It is a frictional force. All right, so that's all we're gonna do for this lab. I believe it should be straightforward other than the little timing. Just make sure that you do it carefully. And also we have a little bit of the calculation for uncertainty, but if you follow these our uncertainty propagation rule, then that should be easy to calculate as well. Any questions? Any questions for today's lab before we end? I want to remind you, you have a quiz today, our lab quiz 3. I'm sorry, lab quiz 2. Lab quiz 2 covered lab 4, 5, 6. Okay, you did 1, 2, 3, that lab 1, and quiz 2 covered 4, 5, 6. Lab 4 is force and motion. If you have a hang mass and a cart and move together. Lab 5 is add wood machine, where you have 2 hang masses run by a pulley, and as one go down, one go up. Lab 6 is conserved quantities. That's where you have the blue and red carts either repel, sort of bouncing collision, or a stick collision. So it will be about those labs. So that is today open until the end of day today. Any questions before we end today's class?
For the sample calculations, like for the bottom, are those are mainly things that we're going to calculate like once we fill in the table? Are they things that are given in the video?
Yes, once you fill out the table, you will use this equation. Because for example, in the table you filled out t, how many seconds? 24/50, for example. And then you will plug in t to get the acceleration right here. Yeah. Any other questions? Okay, all right. If you do have any more questions, feel free to email me, and I will see you, and make sure you do the quiz, and I'll see you next week. Bye, everyone. Have a good rest of the week. Bye. Thank you. I'll see you next week. Bye-bye.